My screen is visible.
Not yet, sir.
Can you see my screen?
Yes,
Yes,
sir.
sir.
Okay. So in radioactivity, you must have gone through how many types of radioactive emissions are there. So the first one is alpha decay. Okay. Alpha decay, or you can say alpha emission. So basically, alpha decay is a process in which your parent nucleus, it disintegrates spontaneously into daughter nuclei, and some alpha particle is coming out. Okay, very simple things. You must be knowing about all these things. So you know that this was first experimentally shown by Rutherford, and he said that alpha particle is nothing but doubly charged helium nucleus. So how we write this alpha? We write it as like, okay. That means this parent nucleus, in this process, what happens? It loses 4 nucleons, and its mass decreases by 4 atomic mass unit, and charge decreases by 2. Okay, this is what is happening during the process. So the equation for this decay is given like this. Let's say this is the element Z A. So when this disintegrates spontaneously into daughter nuclei, then let's say that it is Y, and this is your Z minus 2, is A minus 4, plus He24 plus Q. What is this Q? This is energy. Okay, this is energy. इसको हम disintegration energy भी कहते हैं. Okay, this is also known as disintegration energy. Okay, so Q is the total energy that is released during the decay process, and it is also known as disintegration energy. So how to find out or how to evaluate this Q? Okay, but if you see that from this equation, that if you just see this part, you can say that it is well balanced. But this is not the case. Some extra amount of energy is always released. That is called disintegration energy, and we need to evaluate this Q value. So for that, let us assume that the mass of the parent nucleus be mc. Okay, so mass of parent nucleus, let's say it is mp, and Q is your disintegration energy, and you can write md, that is the daughter nucleus which is formed after this disintegration. That mass is mass of daughter nucleus, that is md, and mass of alpha particle, mass of alpha particle is m alpha. Okay, understood? Now, before this x is converted to y, that means suppose it is at this stage, it is not breaking down. Okay, so in that case, your kinetic energy of this particle x, okay, of this element x will be 0, because it has not disintegrated. Okay, so the kinetic energy is 0 here. And when alpha particle is emitted with certain velocity, let's say it is disintegrated and alpha particle is coming out with some velocity, let's say v. So what is the velocity of that alpha particle? So v alpha, let's say. Then in order to conserve momentum, okay, because we have to first of all derive in terms of classical mechanics. So in order to conserve momentum, the daughter nucleus, it must recoil back with certain velocity. Understood or not? So in order to conserve momentum, in order to conserve momentum, daughter nuclei must recoil back with velocity, let's say Vd, because this is the Md is the daughter nucleus mass. So when it is disintegrated, when alpha particle is emitted with certain velocity, let's say V alpha, let's say V alpha is velocity of alpha particle, velocity of alpha particle is V alpha. So in order to conserve momentum, daughter nuclei must recoil back with velocity Vd. Yes or no? Do you agree with that? So now you have to apply the law of conservation of momentum. So what is the law of conservation of momentum telling you? It tells that initial momentum should be equal to final momentum. So what is the initial momentum? Initial momentum means when you have this one. Okay, that means X is not disintegrated. So in that case, since it is at rest, it is not having any kinetic energy. So the initial momentum will be zero. Do you agree with that?
Yes.
According to laws of conservation of momentum, I can write that initial momentum initial should be equal to momentum final. So we know that initial momentum is zero and final momentum is md vd, and you have to subtract it with m alpha v alpha. Why you have to subtract? Because it is in the opposite direction. That means the direction of this dotted nucleus and alpha particle, they move in opposite to each other. Okay, so from this equation you can find out Vd is equals to it will be what? That is m alpha v alpha by md. Yes or no? Understood?
Yes.
Now we need to find out Q. What we're going to actually find out? We're going to find out the disintegration energy Q. So the energy that is released due to this disintegration process, then that energy will be how much? Final kinetic energy minus initial kinetic energy, isn't it? The energy evolved Q. Energy evolved. This Q of decay is what? Q is equals to final kinetic energy. So what is your final kinetic energy? That is your half md vd square minus md vd square plus, this is for your daughter nucleus and alpha particle, that is m alpha, and this is v alpha square minus 0, final kinetic energy minus initial kinetic energy. Since we know that since kinetic energy initial is 0. So from here directly you can write the equation. I'm not solving this. To solve it and find it out, you'll get Q is equals to half m alpha v alpha square. This is your m alpha by md plus 1. You can give some equation number to this. Okay, I think first equation, let's keep 1. Okay, so this Q is what? This Q is the energy evolved during the decay process. That is the maximum kinetic energy with which alpha particle is moving, isn't it? Are you following it or not?
Yes.
So now I can write, if K alpha is the kinetic energy of alpha particle, let kinetic energy of alpha particle is K alpha, then I can write, this implies K alpha is equals to, or you can write kinetic energy if confused. Write like this, K alpha. So I can write now kinetic energy alpha is equals to half m alpha v alpha square. So if I substitute on in equation 1, let's say this is equation 2, using 2 in 1, what we will get? Q is equals to, this is your kinetic energy of alpha, m alpha by md plus 1. Okay, understood?
Yes.
Yes or no? Okay. So from this equation, what we will get? We can write this m alpha by md. It is roughly nearly equal to 4 by 4 minus a. Here, this ratio of m alpha by md is nearly equal to 4 by a minus 4. Because this is alpha particle, so you know what is 4, what is this a, so you know this meaning. So I can directly substitute this value over here, so that this implies Q is equals to kinetic energy of alpha, and this is 4 by a minus 4. So if you want to find out kinetic energy of alpha, you can write like this, Q multiplied with a minus 4 whole divided by, this is your, I think this is your a. Just a second.
सर वो
This
प्लस
is
वन
your
था तो ऊपर में ये हो जाएगा।
a हो जाएगा ये। तो ये a
नहीं
होगा।
सर, वो वाला तो सही है ना सर?
वो वो तो ठीक था शायद, ये ठीक है ना? 4, so a minus 4, yes, so this is 4, this is correct, I had written. So now this one will be correct. Correct. Here I have to change. This will be a, because this is m alpha by md plus 1. So 4 by a minus 4 plus 1. So 4 gets cancelled. So a. So I think this one will also be a, isn't it, Atik?
यस सर, वो क्यू इक्वल्स
This
टू
will
वाला में ये
be
होगा।
only this one is this. You can give some equation number. Let's say this 3, this is 4, and you can use this 4 in 3, so that is the final expression. So in this way, you can find out what is what kinetic energy this alpha particle is moving. Okay. So this is the final expression, equation 5. And you must have also read about some of the properties of alpha particle. I'm not discussing those things once again. The most important property is that, just I am telling you, listen that. That is that this alpha particle can be deflected by electric and magnetic field, and they ionize the medium whenever they pass through it. Okay, and alpha particle has a very high ionizing power. They can be easily absorbed by few centimeter distance thickness, okay, into the any barriers, let's say aluminum foil or anything like that. Okay, so now let us see that when this alpha particle is, this decay process is taking place, that is daughter nucleus and alpha particle is formed, then during that process, this energy evolved in alpha decay, or that is the Q value, that will share two particles in the inverse proportion. What does that mean? Two particles? That means one is your daughter nucleus, another one is alpha particle. And out of these two particles, what happens? Your first particle is what? Daughter nuclei, another one is alpha particle. So if I take one example, let's say I take an example of let's say AM 241, and this is your 94, is written that it gives you uranium. This is 92, This is 237 plus this is He24. So in this particular like alpha decay process, what happens is this daughter nuclei and alpha particle they share energy, but the alpha particle will carry more energy as compared to daughter nucleus. Understood? So more energy in case of alpha particle. This is comparatively less. Understood? So in that case, whenever we will plot a diagram, suppose we use a semiconductor detector to detect this alpha particles. So in that you will see the alpha spectrum as it will be recorded by this detector. You will see that number of alpha particle is remaining constant for a particular energy value. So the graph will look like this. Let me show you the graph. Is it visible?
No, sir.
Okay. Now,
Yes.
okay, all of you see. So what happens here? If you look at this graph, number of alpha particles versus energy. So this shows that for a particular amount of energy, this alpha particle is always fixed. Okay, though alpha particle is increasing at that particular value of energy, when energy remains constant. What I want to say is that they share the energy, that is alpha particles and daughter nuclei, but alpha particle carries more energy, and that energy is always fixed, even though number of alpha particle is increasing. Okay, many examples you can get in the books. Like if I give you one example, let's say that suppose disintegration is taking place and the disintegration energy in the decay process of nucleus, let's say it is, let's say for nucleus it is 5.085 mega electron volt, and the energy carried by alpha particle is roughly around 5 mega electron volt. So what is the remaining energy? This remaining energy of 0.085 is carried by daughter nucleus. So now can you compare? This is having more energy as compared to daughter nuclei. And the alpha particles which are emitted during this particular decay process, if we take this example, then we can say that all the alpha particles emitted in this decay, they have same energy. How many number of alpha particles it may be, but the energy is same, this much, 5 mega electron volt. That is why if you draw a graph between them, you see it is a horizontal line, sorry, vertical line. Okay, that is called your energy spectrum. This graph is called what? This graph is called energy spectrum of alpha particles. Okay, understood? Is it clear?
Yes.
Okay, so what is the range of this alpha particle? Have you read about the range? Range means the distance moved by the alpha particle in a given material before it comes down to rest. Okay, up to what range it can penetrate? Penetration range, penetration depth. Okay, so what happens to that? This range is defined as R. Okay, it is related with your initial energy of alpha particle. That means more the initial energy of alpha particle, greater will be the range. Understood or not? More is the initial energy of alpha particle, greater is the range. More the initial energy of alpha particle, greater is the range and vice versa. Okay, that means if you take any medium, let's say air medium, or if you take any material medium, let's say if you take aluminum or you take iron, so this range of this alpha particle, this R value will be different in all the cases. Okay,